everyone! So, last time we touched upon build systems, which are used to help us build the code. And we mostly have been looking at make and at make files that are related to that. But as I hinted before, this system is really not enough to build big projects. So in order to build big projects, you need something a little bit more abstract. And in this course, we will mostly be using CMake, which is what this lecture is going to be about. As you guys all know, I use the special symbols that I leave on the slide now. Feel free to return to them if you want to, but today we're going to be talking about CMake. And CMake is basically one of the most popular build configuration and generation tools. It is designed to solve the shortcomings that I described in the previous lecture about make. So CMake is extremely powerful, and the script that you use to generate your build is still very readable, and that's the main benefit of CMake, if you ask me. But I just want to straight away get rid of this confusion, because CMake is not really a build system, it's a build generation system. Now, what does it mean? It means that CMake itself, it does not build the code. It just generates files for another build system to build. And this other build system can be either Make or Ninja or any other form of a build system. We will be using Make in this course mostly. So now let's dive into CMake, and we will start by talking about the intuition to CMake. What is it all about? The first thing that it provides you is an access to your host system. Basically, it allows you to know if you're running it on Windows, on Linux, or on macOS, and also what environment it runs in. The second thing it does, it configures your build, or more precisely, it configures variables for your build. And the final thing that it does, it generates the correct commands for the compiler to run in the form of a make file or anything else. So what this generation comes down to internally in CMake is it defines the library and executable targets, it defines their dependency graph of what depends on what. Finally, it specifies the correct build and linking flags for all of those, and in the end of the day, it actually generates the commands that are needed to build all of those files correctly. So the whole build process is defined in a CMake lists.txt file, or potentially multiple of those. But the most important thing about CMake, and if you remember one thing from this lecture today, remember this, that CMake is just a scripting language. It means that when CMake program is reading the CMake lists.txt file, it reads it from top to bottom. That means that the commands that show up higher in this file are going to be executed before the commands that are lower in this file. Apart from this, as any scripting language, it has its own way of encoding the logic, which means it has the functions, it has the control structures, and it has variables and everything like that. But it also has some CMake specific quirks, which is why we have this lecture here. And to start talking about the specifics of CMake, we have to start with the minimal project. So what is the minimal thing that will do nothing useful, but at least you will be able to run CMake on? And for that, you will need to specify two commands in CMake. And you put them into a CMake list.txt file. The first one is CMake minimum required, and the second one is project. So the CMake minimum required just basically defines the version of CMake that you account for. And you can provide either one version, which is the minimum version that you tested your code with, or you can provide two versions with the two dots in between, where you say, well, the minimum version of CMake is this, but the maximum version is that. The second command that you have to call is project, where you basically define the project that you are building, and it has to have a name, it has to have a version, it can have a description, and you can also provide languages which you're using, so something like CXX for C++ or C for C. And there is a bunch of other languages out there that you can use. But if you leave it empty, by default it's going to be C and C++. So now that we have this file defined, let's look at how can we run CMake with this file. So having a project with just a CMake list.txt file, we can pass the folder with this file to the CMake binary.
CMake then does two things. The first one is called configuration, which reads all the variables found in the CMake list.txt and creates a CMake cache.txt file with the values of all of these variables. It is called a cache. The reason this cache exists is for the user to be able to look at it and to potentially change some values in this cache. If and when CMake cache.txt already exists, CMake just reuses it and assumes that the values there are final, so the values of the variables in the cache have precedence over those defined in the CMake lists.txt. When the configuration is done, the second step is generation, where CMake follows the structure defined in the CMake lists.txt, takes all the values from the cache, and generates the appropriate files for the underlying build system. Now let's look at an example that shows all of this. We use the same simple project as we just discussed in some project folder, and we start with this simple project with a single variable foo set to the value of foo. We set the variable that lives in the cache with this command, set foo cache string, and then we provide some description. We can also print the value of this variable using the message command, like so. We print the message, status, value of foo from cache is foo. Note that we use the value of variable foo just like we do in bash with the dollar and the brackets. We could also use warning or fatal error instead of status here, depending on the context.
So the difference here is that when the warning is encountered, it's going to be shown in different color in your terminal, usually. And if the fatal error is encountered, then CMake will actually return an error code once it's run, because the build was not successful.
There are two ways to build this project for us. To use the CMake program, which configures and generates the build in one go, or to use the ccmake program, that provides a text user interface and decouples these steps. Let's try both of these. We have to run CMake command with two flags. The -s dot, so to provide the source folder where our CMake lists live, and the -b build. Basically, we provide the build folder. That's the folder where CMake will generate all the files it needs for the subsequent build of the underlying build system. We can now see that it prints the value of our variable along with some other things. Let's have a look at the folder tree again. We see there is a bunch of files generated in the build folder now, because CMake does both steps, the configuration and the generation step. We will also have a make file in the build folder. You're free to look at it. It is a bit complex, but you should be able to understand most of it after we learned about make files in the previous lecture. To run the underlying build system, we can use the CMake proxy command, the CMake --build -j12. The build parameter that we provide to the --build flag here should match the folder build that we used before. It does nothing for our simple project, but that's all we have to know about building any CMake project.
Now, I just want to mention this very shortly because you will see this all over the place. In the older CMake, I think before 3.13, if I'm not mistaken, you would have this process look a bit different. The process would be the same, but the commands are a bit different. And I just put them on the slide here, so feel free to look at that. And I hope that at this point it should be understandable what happens there, so I won't go into details.
Anyway, for now, talking about variables, we mostly care about the CMake cache.txt file that is found in the build folder. That's the file where CMake stores all the variables cache. If we open this file with a text editor and look for foo in it, we will find it along with the value foo that we set to it. Let's change this value in this file to updated value instead. Now, if we rerun the CMake -s.-b build again, we see that the new value is printed to the screen, even though the value set in the CMake lists.txt file is still foo. So the command sets the value of a variable if it's still not set in cache, and does nothing if it is set. This is one of the main confusion points, and if you remember this, CMake variables won't confuse you as easily. Now let's do the same with the ccmake command. First, to clean the build, we just remove the build folder, then we can run ccmake with exactly the same flags as CMake, so the -s dot and the -b build. It takes over our terminal to show us the user interface. At first, it doesn't show us much, just a couple of options of what to do, and most important being the configure and the generate steps that we can make. Let's configure the project now. It shows all the variable values it found. Star means the value has changed since the last configuration, and allows us to update them without needing to modify the CMake cache.txt file directly. Let's change the value of foo to updated value again here, and reconfigure the project by pressing C. We can now quit ccmake by pressing Q and inspect the CMake cache.txt file just to make sure. Note that because we only did the configuration step, there is no make file in the build folder yet. Let's start the ccmake program again. We can see that the variable still has the value we set to it. We can now generate the build files by pressing G, which closes ccmake. Now there is a make file in the build folder, just like after calling CMake. In both cases, we can set the cached value of any variable directly from the command line using the -d flag. In our case, we can set foo like so: cmake -s dot -b build -d foo command line value, or cmd value. See that the provided value is actually printed to screen. If we want the value to always be as it is in our CMake list.txt, we can do this by adding the force keyword. Let's copy the line we have and print the value after forcing it. See that the forced value is printed to screen as expected, but also let's have a look at the value stored in the CMake cache.txt file and check that we forced our value there too. Sometimes we want the value to be set in our CMake list.txt file, but we don't want it to be set in the cache, and there are two ways to achieve this. The first is by using the keyword internal. So for example, we can set foo to some value, and then we say cache internal. Like this, we still keep it in the cache, but we mark it so that it's not shown to us in the configuration step. See that this value is not found in the cache anymore. The only line we find here is the one with the comment before it. By not using the keyword cache at all, we can make it a local variable. So if we just type set foo to some value, that sets a local variable. It overrides any variables in the cache with the same name from this point on in the CMake build script. The value of foo in the cache remains the same as before, and we can check that easily. And the value of foo before the set command will still be the one from the cache. And that should be all that you need to know about variables in CMake.
And now we get to the meat of CMake, how to create libraries and how to link them to other libraries. We start by creating libraries. To create a library, you have a very logical name for this command. It's called add library. Now, for example, if I want to create a shared library, I just write add library, my library, whatever the name of my library is, then the keyword shared, and then I provide all the sources that I want to use to generate my libraries. So I just care about the CPP files here, the header files we're going to talk about a bit later. If I want to do the static library, I do exactly the same things. I just say that it's a static library. Now, the only different one from the batch is the header-only library, and to create that, we use the keyword interface instead of the shared and the static, and we don't provide any CPP files because there are no CPP files in a header-only library. Please note that all of the paths are relative. And if you want to use an absolute path, don't hard code your absolute path into there. Use the variables provided by the project command, something like a project source dir here, instead. If you do not provide the static or shared explicitly, then this will be guided by the value stored in the variable, I think it's called build shared libs. So if build shared libs is true or on, then every library will be shared, and if it's false, then every library will be static. The story is very similar, but even a little bit easier when you want to create an executable. You just call an add executable with the name of your executable and then the file that you want to compile as your executable. Please note that this file has to have a main function in it. So now we have our libraries and our executables defined, but they still don't have any properties to them and they're still not linked together. Before we talk about linking them together, let's talk about their properties. And the properties can have basically three visibilities. They can be private, public, and interface, and they are defined per target. Every library, every executable is a target. Please note that targets created with the interface keyword, like header-only libraries, can only accept interface properties. And generally there is a bunch of commands that we can use to set different target properties. All of those commands look something like this. The command that we use, the target that we specify, then the visibility, and then the properties that we want to set. And the difference between the public, private, and interface is the following. So if we set these properties to a particular target, then the properties can be used already for this target, for my target in this example, or for the targets that rely on this my target down the line. And if we use the public properties, then they are available to my target and to the descendants of it. If we use the private, they're only available to my target, but they're not going to be seen downstream, down the line from my target. And if we use interface, it's actually flipped, so my target cannot use these properties, but they are going to be visible downstream. So now we're ready to talk about the dependencies between the targets. And this is another very important part of CMake that a lot of people get wrong. And largely it's because of a name that could be better. So here we're talking about the target link libraries command. To use it, we specify the target that we want to link against another target. We specify the visibility, the public, private, or interface, and then we specify all of the libraries that we want to link to our target, my target in this example. And my target can be either a library or an executable. The main confusion point here lies in this name. So just reading the target link libraries, you might think that it only handles the linking, but it's not. It's actually handling all of the dependencies. It's basically propagates all of the dependencies of any target that you put on the right of this command to the target on the left of this command with regard to the visibility, of course. So it's not just about linking, it's actually all of the properties of those targets. And if you remember that, you're going to be fine with CMake. Now, let's talk a little bit more about these properties. What properties are there? Well, they kind of map to the things that we care about when we do the compilation. We can set the compilation flags for the includes, something like the -i flag, and we do that with target include directories. We can actually set the linking flags, the -l capital and -l small one, with the target link libraries. So that's actually what it does too. We can also set some compilation features. So if you want C++17, we can use the target compile features. And finally, if there are more flags that we want to set to a certain target, we can use the target compile options there. And one more thing that I wanted to talk about here is when to use which visibility. Generally speaking, you should use private visibility with all of your executables. In most cases, you want the public visibility with your shared or static library targets, and you use interface visibility with your header-only libraries. And it's important to remember to always use the visibility when you're setting properties for your targets. If even one property doesn't have the visibility, all the downstream dependencies will not have visibility for it, and it makes your CMake files so much harder to understand and to read. So please always set the visibility whenever you're setting any property to any of your targets. And now it's time to follow up with an example. The example is going to follow this following project structure, which is kind of a typical project structure. At least that's the one that I mostly use for my own projects, with slight variation here and there. We have a project folder which is called Our Project. That's where all of the files for our projects live. It has a CMake list, which basically defines our whole build. And then there is a bunch of folders. So these folders are usually something like executables, which holds all of the executables of the project. They can also be called examples in different projects. Then the most important folder is again the our project, so the name of our project repeated. And the reason we want to repeat this name here is to maintain a very nice and consistent include path for all of our includes. We'll see that in a second. Then we have the build folder, which is something generated by CMake directly. And then there is a bunch of other files which are useful for the project maintenance. .git is generated by Git. You should not create it on your own. The .clang format defines the clang format rules that clang format will use to format the code in your project. Then there is git ignore, which just helps ignoring certain files in Git. And finally, a very important file, the readme.md, that's the interface to your project for the user. So when somebody opens your project, that's what they will first look at. What it does, how it does it, and how to run it. Now let's dive a little bit into details here into the Our Project folder. You can see there is another CMake lists, and then there is another CMake lists in the Tools folder right there, which is where most of our code lives. And we will do exactly the same example as before. We will try to write a Hello World program. So we have this library tools, and we want to link it to the print hello. You also see there is a test file in there, but for now we're not going to be filling this in, and we'll leave it for the future videos to come. Also, I just want to give a small hint here. You can see this folder structure, and it's generally a good idea for the namespaces to follow exactly the folder structure. That's the way to minimize the possibility of name collision for your variables and functions and whatnot. So let's first look at the C++ code again, and I will not stop in details here. So we have this print hello function, which we declare in the header file and we define in the CPP file, and then we want to use it in the main function of our print hello.cpp. So everything standard stuff. And then the main interest for us here is how do we put it all into a CMake list. So let's first look at our main CMake lists, the one that lies in the root of our project. So this file starts with the stuff that we've already seen, basically telling which version of CMake we expect and the project name and which languages we use in the project. We've seen that before. Now the next part is something that we haven't seen before. It has some logic to it, there are some if statements and some setting of the variables. The CMake build type is a very special variable in CMake. It defines which type of build we want. It can be either debug or release with debug symbols. And basically the difference here is the release one is going to be the fastest one, so with all of the optimizations enabled usually, and the debug one is going to have debug symbols in it, so it allows us to debug the code after the fact, like after we've written it, and we want to find some bug. Generally speaking, it's not set by default, and CMake wants you to set it on your own at every single configuration. But what I like to do is to have this check. If I do forget to set my build type, I want it to be set to a release by default. But if I do set it from the command line, then this will not trigger, and I will not go into this if loop. Okay, so that's all that you have to know about the CMake build type for now. And then there is the add library, which is an interface library, and it's not really a library. It's just another target with an interface property that has a lot of different properties that we want to basically maintain throughout our project. So for example, it has these flags that handle the warnings, it has the setup for the C++17, and it also has the include directories in there, so that all of the includes are searched with respect to the project source directory. Finally, this file ends with two add subdirectory commands, which basically just outsources the actual creation of actual libraries and binaries to the downstream files, to the downstream cmakelists.txt files. And we do omit a couple of things here, so we don't create any tests and there are no install targets. But generally this is a good look in CMake lists that is going to bring you pretty far already. And everything that we missed here we will cover in the future videos at some point. Now let's look at the CMake lists.txt file in the subfolders. The one in the Our Project subfolder is going to be very simple. It just adds the tools folder, and the one in the tools folder is actually the one that creates our library. So what does it do? It basically creates the tools library. We don't specify if it's a shared or a static library. We don't care about it right now. And then what we do is we link it to the CXX setup one, which is our interface, well, kind of target from the uppermost CMake lists.txt, which is basically just propagates all of those settings or properties that we set to the CXX setup to be used also here. And finally, in the executables folder, we create the executable and we also link it to the tools library as well as the CXX setup. By the way, what will happen if we omit the CXX setup here? Write your answer in the comments and let's discuss. And that's it. Now we can actually build our code, and we build it in exactly the same way as I showed you before. So we go to the project folder and then we call the CMake with the source folder and the build folder provided. It will generate the build files that we then have to run, so the make file in our case, and then we have to call the CMake --build, which will under the hood call make on our make file, and that should build our code. From that point on, we should be able to find the executable and run it. And I really urge you to copy over that code. You can either just type it in, which I suggest you do because that's the way you remember better, or as always, all the code is in the slides repository, so just follow the link under this video and copy it over into your editor. But I really urge you to really do this example on your own because that's the way you understand it better and you remember it for the future. One final thing we have to discuss here is how to clean the build, and it's actually extremely easy if you follow the good practices in CMake. You just remove the build folder. And that's partially the reason why I suggested to always use the build folder in your builds. Now you just remove that and you have a clean build and you can start from scratch if you messed anything up. And on that, you now know the basics of CMake. You now know how to create libraries, how to link them to other libraries or executables, and how to build the whole code, and actually follow already a pretty good style there. There is still a couple of things missing here and there, but don't worry, we will cover them in future videos when we need those. So thanks for your attention and see you in the next one. Bye.